Welcome to the Fizzix2 How-To software. This is the introduction to what will be a 5-part series that will demonstrate the usage of the Fizzix2 software. First, before we get into how to use the Fizzix2 software, let's explain what the Fizzix2 software is. The Fizzix2 software is a simulation tool that uses new electromagnetism version 5 field models to compute forces and/or voltages between wires, magnets, and charges. Okay, and this is the simulation of experiment. This is a similar experiment, not the exact same one. You can tell these are the codes. 2 means it's the paradox 2 magnet configuration where the magnets are parallel to the wire ring. Q means it's the Q wire format. I means that the second magnet is inverted, and S means that this bar here is stationary. Okay, and this is the 2QIR, which is, it just means that the center ring here is rotating with the magnet. Okay, so everywhere you go, you get these 4 character codes which represent the experiment. For the paradox 2 through 3 series, there's over 54 different experiments. And this for the 4DNS, okay, this is the 4DNS experiment. This is paradox 4, where the magnet configuration is perpendicular to the loop. This is the D-shaped loop, no second magnet, and the D is stationary. That's what the S means. In this, the measured data is the red. The computed data from the Fizzix2 software. The Fizzix2 software allows you to separate effects so you can see the contribution for each of the effect. In this particular example, the inertial force is the blue. The magnetic force is the green. And when you sum those together, you get the black. And as you can see, the experimental data lays right on top of the simulated results. Okay, like I said before, the paradox 2 through 4 series has 54 different variations. The black dots represent the simulated results for all those experiments. And the red dot is what would be the measured results for all of those experiments. And you can see it's dead on balls accurate. Okay, so one of the special features of the new Fizzix2 software is that we have nested inertial and rotational reference frames. So you can have a rotational reference frame inside a rotational reference frame inside a rotational reference frame, and it will compute all the Coriolis and centripetal effects of all of the objects attached to any one of the reference frames that are in motion. Okay, again, all effects are separable, allowing analysis of individual contributions. And we also have special sensor viewing film or sensor plane, which allows us to see the effect of the forces over a given plane, where little arrows show the direction of the force and the color represents the intensity of the force. And you can tell this viewing film to ignore, either you can filter out which effects you want the film to look at. So if you want to look at only the inertial effects, you can program the film to do that. Presently, I use it to just give me the total of everything. I haven't really used the feature where it separates anything out yet. Okay, so in this video series, there are actually 6 videos right now planned. This one is the introduction with setup and a simple example. The next video, we're going to go into detailed description of all of the components that are available for simulation. In the third video, we're going to look at all of the available effects and how to compute effects, forces, and VIMs between objects that are in the simulated environment, how to pull data out of the simulated environment for analysis, let's say in Excel or MATLAB or whatever you want to analyze it in. Okay, number 4, we're going to show how to do sequences of measurements like an animation. I'll show you an example of that, what I mean by a sequence of measurements. And then how to make your own components. This is going to be quite complex, so if you don't understand anything here, you're not going to understand this. And finally, a description of all the built-in experiments. So with the Fizzix2 software, you're going to be getting all of the experiments that are presently there supporting new electromagnetism V5, and you'll be able to tear them apart or whatnot. So in this video, we're going to look at the installation, the needed libraries. We're going to look at the environment, which are the namespaces, Then we're going to do a simple example, and then we're going to give you detailed lessons on how to pilot the viewers to fly around the simulated environment so you can observe your experiment at different locations to see if you've implemented all of the vector logic correctly. So let's first look at installation. Okay, the software will be released shortly or later, depends on what the Patreon upper tiers want to do. I have a poll out for them that will close the weekend of October 19th. And if they want to release the software early so that the upper tiers can follow along with the video series, that's one option I gave them. The other option I gave them is to release it at the end so that all the examples that I put into the tool, I can release with the tool. So they'll get the examples that they see. So that is, so far the polling says they want it to be released at the end of the video series. Okay, but when it is released, okay, and right now it'll be available to Patreon engineers and above. You search for the Patreon tags SW for software and Fizzix2, and you'll have a zip file that you download the contents and unzip it to Fizzix2, or just download it to the direct. It doesn't really what you call it. Just download it to a location you're familiar with. It doesn't really matter. This is typically where I put it. Now, the needed software that is needed to run the Fizzix2 is Visual Studio 2013 or above. Now, with this said, this is the software you're going to need to edit and to put in your own experiments and to look at the code with. There'll be a later release, I don't have a date yet, where I'm going to release just the executable to the first class passengers and above so that they can execute the experiments that come with the software to derive their own, to see the data come out their own. But that's a low priority item, which will come out sometime in the middle of the cosmology video series. Okay, so ultimately though, any version of Visual Studio that supports Target Framework 4.5 for C#. The next thing you'll need is SlimDX. And if you go to this link here, Google.com archive pin, SlimDX. If you just look it up on Google for SlimDX, it'll pretty much get you. That's how I got this link. And the only thing you need is the very first link up here. Later on, when I release the executable only, you're going to need the runtime. I don't know which runtime I'm going to build. I think I'm going to make the runtime for x64. This guy here supports both x64 and x86. Okay, so this is all you need if you're going to be running with the Visual Studio. Okay, the environment. Okay, it's broken down into two parts: the application and the library that comes with it. And the namespaces in the application is Fizzix2, and that contains the main GUI and all of the experiments and simulations. What I've done is I've separated the math libraries, which is Vortex and Vector, the Fizzix2 basic objects and the Fizzix2 interactions into a Fizzix2 namespace. The wrapper around the SlimDX, which is called Draw3D, that is separated as well, plus some other standard utilities. Now, the reason why I kept these separate, and I'm not releasing the source code for these, is because in the future, when I have to replace the SlimDX with some other drawing tool, I can replace it just by updating the library. Instead of having you have to change all of your code, you just have to link to a new library. Also, if I find that there's errors in Vortex, or if I find that there's errors in the Fizzix2, I can release an updated DLL without having you to merge changes into a full application that has all these things linked. So that's the main reason why I'm keeping it separate as a DLL, so that I can maintain the core. And you'll still be able to see and run everything that's in here. It's going to be basically version controlled. Okay, and then the working directory. Let's go to the actual code here. Okay, so when you run the code, the first thing it's going to come up is going to tell you this is version 2.01D. That means it's being built as a debug. I think the release I'm going to release as, well, no, it doesn't matter. When You run this, you can build it as debug or release as you like, but the components you get are probably going to be built as release. Okay, but the important thing here is the working directory. There's a lot of these experiments, and we'll talk about all the experiments later, like the homopolar or all the paradox experiments, parallel wire experiments, charge motion experiments. These guys will dump stuff out to a working directory because they dump out lots of stuff. And what you have to do in the beginning is specify yourself a directory where you want all this stuff to go. Now, you can change it anytime you like by doing this guy and then selecting a directory. But I think the easiest thing to do is, because you'd have to do that every time you power up, if you instead you go to the foundation down here and just change this guy, then you can make the default working directory anything you want when you power up. Or you can just go to your C drive and just create a test directory for output. That's what I have right now. This is my test directory. I got some of my old dumpages from some of the old paradox experiment dumps. So there's some of the graphics and stuff. Okay, so that's the first thing, is we're getting the working directory squared away. Either you override it in the beginning, or you just create a C-test directory, or if you want to put it somewhere other than C-test, either override it every time you come in, or you can override the default in the foundation class here. Okay, so the working directory needs to be taken care of. And what's next? So let's do a simple example. Not here. Okay, let me just show you some other things here before we get started. These are your general purpose buttons. This is checkbox A, B, C, D, text box E, F, and G. Later on, when I explain some of the experiments like, charge motion or the paradox, you specify the experiment you want in label E, and then in text box F, you put the number of points. Let me show you an example of what we mean by that there. So if I go here and I want to run the 4DYS experiment with 50 points, okay, you have to know what the codes mean of which paradox experiment you want. Then you run this guy. And let me open the viewer first. Let's open the viewer. Now, when you open the viewer, you have to, and I'll show you how to pilot it. Right now, when you don't have an experiment in the universe, you get this blank blue with this little test triangle. That means you haven't loaded an experiment. So what I'm going to do now is I'm going to run the PDX using this guy. So this is going to come up with the 4DYS, and it's going to run 50 points. That's 1, 2, 3. And if you look in your test directory, where is it? There it is. You see that this experiment is being run, 4DYS. Okay, and there's a picture of the experiment here. If you go in here, when it's done, it'll dump out a whole bunch of data in here that you can analyze. And however many viewers you have open, it'll give you a screenshot of that viewer. Now you notice that the edge currents are turned on. I'll show you how to turn that off. The edge currents are still there. It's not displaying this ugly purple wire here. Okay, I'm not going to wait for 50 points. Okay, 200 points is a full circle, so 50 points is a quarter of a circle. Now, unfortunately, processing is done in the drawing thread, so your application will get sluggish until it finishes the simulation. I never made plans to make it anything more than a way to verify there it's done. Okay, and this is what you get in the directory. You get Excel spread. Now, these are CSV files with the different data and a picture. If I had 2 or 3 viewers open, it would give me a snapshot of 2 or 3 viewers worth of data. Okay, you can even tell it to do a sequence where it'll take a picture every turn so you can actually do an animation with it. Okay, so that's the basic overview of the controls and how the experiments run and the importance of the test directory, or the working directory rather. If you want to run all of the Paradox 2 experiments, you would just go test Paradox 2 and you would say do all for either 10 points or 200 points, but it'll limit some of these to 10 because some of them are no-brainers. They're all 0, so no sense running 200 points. Are all going to be 0. So this thing will run those points that are definitely 0, only run them 10 points along the circle. Okay, so that's the general overview of the controls. Here is a selection for the models you want to run. This is the V5 and this is the V5.2. That should have been corrected instead of 5x to 5.2. And the only thing the 5.2 has more than the 5 is has the anti-gravitic force in it. That will give you pretty much a null result when you run the anti-gravitic experiment. Now, don't worry about it. All of the stuff that's up here right now, we're going to have a whole video that's going to go over every one of these things in detail later. So I'm just giving you a quick overview of what the controls are, and here have all the experiments. Some of these are just visual aids, and again, we're going to cover all of these built-in experiments in like the last video. So once you're familiar with how to write a simple experiment, then it'll be easier for you to go in and understand what all these experiments do. So don't worry, we're going to go over all this in detail in the later videos. For now, let me just show you how to write put a simple thing in the universe, just to get you started. So we're going to stop this guy. We're going to put this guy off to the side. We're going to bring up our thing. Now this guy that we just saw here, this thing in the software, this is called Form 1. Whenever you have an application, a Visual Studio application, and you put down a form, it's always defaulted to Form 1. I don't bother renaming it. Form 1 is as good as any other name for the main form of the application. Okay, so then what you do is you go to your Solution Explorer, you hit View, Solution Explorer. Okay, it's already up, and you go down to Form 1. Okay, now what I'm going to do is I'm going to add another thing for examples here. So I'm going to add for examples. And this will be available if the patronage decides they want the video released, the software released at the end. Okay, so we do that, and I'm going to put in, let's do the first one, just a simple magnet. Simple magnet. Let's just put a simple magnet in the universe. And then to create a handler for it, you double click. Okay, so now we have a handler. So what we're going to do, the very first thing you do is say clear it should be clear the universe. Oh, my universe clear. Okay, so my universe is the universe. We're going to make sure that there's no pre-existing stuff in the universe. Okay, then what we're going to do is we're going to create let's say a disk magnet. So it'd be magnet. These are all experiments. So there's a disk. Okay, FZX2 dot disk. There it is. Okay, so I have to use the namespace to get out a F2 magnet disk. My disk. Okay. Now what we want to do, now when a magnet is created, its default position is the origin. It has a default size, it has a default current, it has a lot of default stuff. For now, I'm just going to keep all the defaults, and then I'm going to say my universe, add Good if you spell it right. Okay, now I added this magnet to the universe. And the only thing I have to do is grab some of these guys. Okay, on construction change goes in, and for all of the objects, whenever you change any of the construction parameters, you have to tell the universe to update. You can either tell the object to update its construction, or if you tell the universe to do it, the universe will call all the objects in the universe and tell them to update their construction. Okay, and this one here is update for input parameter change. We'll update the physics, but we're not taking any measurements. And then this one will refresh all the viewers. Okay, so we probably don't even need all of those. We could probably get away with just this one there, because we haven't done anything more than just add this thing to the universe. So let's go F5 to run. And what I'm going to do is I'm going to open the viewer first. And then we're going to do the example, simple magnet. And it didn't work. Oh, I know. I have to update the experiment. There it is. Okay, now the reason why I had to do that, if you don't want to have to do the update, you just have to move. Let me see. Go down. There's our magnet. It's at the origin. Okay, it's the south side of the magnet's up. That's interesting. You'll notice that this one doesn't draw the little edge current. Let me show you how to fix that. So now the other thing we're going to do is this guy here, by allowing him, he will cause all of the viewers to update automatically. See, what I did when I said add the magnet, I had to make the viewer move before it would update the display. This will force the displays to update automatically. So let's change one of the parameters of this. Let's cause this to draw the little edge current. My disk dot draw edge currents equal true. Now the edge currents are there whether you draw them or not. The draw is just there for demonstrating, where the location of the edge currents are. So let's go F5 again to launch, to run. Open the viewer first. You can open the viewer afterward, it doesn't matter. Okay, and then simple magnet. Now if I go down, oops, make sure you select it. It didn't draw the edge currents. What's going on here? Did I need that guy? Oh, I guess I needed that other guy. Okay. All right, so you can see, so you should do all of these guys. So you can see it puts that stupid, pukey, purple edge current there. And the one thing we can show you that the center of that is where the edge current is located. So if we go in close and then rotate. Okay, so you can see that we're cutting into the edge current, and right where the green and the red meet, that is the center of this edge current representation here. So that is the location of the edge current. Okay, so that's a simple example. And the other thing you can do if you want to change the direction of the current, then you just say my disk I. this is the current in the disk magnet, equals, let's say, minus 1,000 amps. That should change, unless it was already negative. Yeah. Oh, no, it was negative already. Okay. Let me do this. Let me change this. So you can update. You can actually, hold on, let me do this. Now let's do that. I'm going to put a breakpoint there, and I'm going to tell it to, oh, damn it, obsessive clicking disorder. Okay, add it again, but now I'm going to change. So you can change the code as long as you breakpoint it. Okay, so the reason why it had the red up to begin with before is because the current defaults to 0 in the magnet. So if you put a positive current in the magnet, and the normal coordinate system of a magnet is it'll be centered at the origin with the north side up. So let me show you the coordinate system here. Okay, so when you put a new viewer in, let's start a new viewer. And what I'm going to do is just back away. I'm going to hit the 5 key on the keypad. Okay, so the viewer starts. When it starts, the viewer starts at the origin, and the viewer starts looking in the minus Z direction. This is the plus X, this is the plus Y, and the viewer is now has moved into the plus Z direction. Now you can identify these. Okay, you see these colored lines here? Let me go away. And let's do that. Okay. So the red is the positive X-axis. The yellow is the positive Y-axis, and the cyan is the positive Z-axis. Okay, it's orange for the negative X, green for the negative Y, and I think it's purple or magenta for the negative Z-axis. Okay, this grid here is in centimeters. Okay, so if I wanted to change the dimensions of the magnet, the dimensions are in meters. So let's do that. Let's put a breakpoint here. And we'll tell this guy to add again. Okay, and so what I can do now is say my disk dot diameter is equal to, now this is in meters. Everything you do in here is in meters. So meters dot centimeters. Let's make it a 6 centimeter diameter magnet. Okay, and my disk dot height equal. So if you just want to put the meters in, you can put 0.06 to get centimeters. But what I have here are converters that allow you to get meters from centimeters, get meters from inches. Let's make it 1/8 of an inch high. You know, so you can mix and match whatever units you want. This little tool here will do the conversions. We have other conversions too for rotational speed, angles, yada, yada, yada. We'll cover more of those later. This is just a simple introduction. Now let's hit F5 to allow this to continue. And we look now in our viewer. Now our magnet is 6 centimeters in diameter. And its height is about 1/8 of an inch. And let's turn off that silly, oh yeah, so we gotta tell it to add it again. So let's make this false and then hit F5. Okay, and that silly edge current is gone. Okay, the reason why I have it either print the edge current or not print the edge current is when I was doing the simulation for motions, I had an instance where the north and the south facades here were spinning in one direction and the actual edge current was spinning in the other direction. Because the actual edge current in here is actually made from the same wire filament construct that we use for wire filaments, except that the centripetal and the Venturi effects are ignored because there is none in the magnet. Okay, now that we have a basic, input showing you basically putting something in the environment, we're just going to show right now, finish this up by showing you how to actually fly around the universe. Okay, now that we have something to look at. All right, so now what the viewer does, the viewers use the keypad. Okay, make sure the num lock is turned on. If the num lock is turned off, it's not gonna do anything. Okay, and so what you have is the 5 key is move back, the 8 key is move forward. These are the greens are the translators. So this will be translate left or slide left, however you want to say it. This is slide right, slide forward, slide back. This is turn left, turn right. These are basically your yaw. This is nose up and nose down. That's your pitch control. And this is roll left and roll right. Those are your roll control. Now, as I was redoing this, I realized that we also have a move up and a move down. We have those assigned to other keys, and I didn't realize I could just assign them. These aren't working right now, but before I release the software, I'll update the code that the asterisk key is move up and the dot key is move down. And then we have these two buttons for plus and minus to increase or decrease speed. And let me show you what that means in a second. So let's go back to the viewers. Oh, let me show you the other keys first. So the arrow keys will do the same thing as the 8 and the 5 key, move forward, move back, and the 4 and the 6 key, turn left, turn right. If you hold down the control key, this is where you get the move up and the move down, and the move left and the move right. Okay, but you only get those with the control key. And what I'm saying now, what I should do to make them available on this keypad, I'm going to make these keys also for move up and move down. Okay, so let us go back to the applications. Okay, so again, the 5 key. Oh, I can put that guy in the background for help. Wrong one. What the hell is this? Oh, I can start it over from the beginning. Okay. So I'll put this over here. So again, the 5 key moves away backwards. The 8 key moves forward. The 7 key slides left. The 9 key slides right. The 4 key turns left. The 6 key turns right. Matter of fact, let me come down a little bit here so you can see that. Okay, here's the turn right. Here's the turn left, turn right. Okay, here's roll left. Here's roll right. Again, nose up, looking up. The 2 key is nose down. And then if I hit the control up arrow, I start sliding up and I start sliding down. Now, for the decrease speed and increase speed, watch this. So you see, if I get in close, and I rotate left, and I rotate right, you're like, well, gee, I want better precision. I want to be able to, so if I hit the decrease speed a couple of times, then every keystroke has a much smaller effect. Okay, so if I'm backing away, see how slow it is? So if I increase, hit the plus speed a couple of times, see how fast that was? So you can change the speed and the resolution of turning or sliding. using the plus keys. And most of the times when I'm using it, it's because, you know, I got too far away or too close and I can't get right on. So if I decrease the speed, then I can get in real close and real fine units to slide in real nice and real tight. Okay, so that's the purpose for the increase and the decreased speed. Okay, the next part is the part that I'm going about. Okay, we have the F keys, the function keys. So if you want to save your camera, you got that perfect camera location every time you restart your software. You know, you want to look at your experiment from this particular camera location angle. Well, you can save your camera location. To save a camera location, you hold down the Shift key and hit any one of the function keys. Well, right now only up to F10 work. My notes is to get it to work for 11 and 12 too. So you hold down your Shift key and I'm going to hit F1 to make this my first camera location. So then if I go run over here now, let's go run over here, and I go run away. If I hit the F1 key now without the Shift key, it'll bring me back to that camera location. And these camera locations will persist. So here's my other camera location. If I want this camera to go to the same location as this, I just hit the F1. And now he's got the same view. Okay, and so, and of course, so you can, it's not saved per camera. So you can save all your favorite camera locations. So every time you start up, you can put all your cameras in the location you like. Okay, and these camera locations persist between runs, but they don't persist for each user. So if you have a person that logs on under a different account, wants to use the software, they're going to have completely different camera locations. They're not going to be able to obtain yours. Now, if you want to be able to set somebody's camera location, you hold down, just hit the P key, then you get a screen dump of your present camera location. But right now, I don't have a way to save that off and put it back in. I just never really had the care or desire to do that right now. There's just been no need for it. The main reason why is because in the programmatically you can move the cameras any way you want. Okay, but maybe I'll prove that later. Okay, so last thing to show you is the ability to take screen captures. So we're going to move back out, and in order to take screen captures, you have to hit the Control. Let me go to the help page here for that. Control S sets up the screen capture, sequence capture, and Control C captures a frame. Control S. Oh, it's under test. Oh, it's on a different drive. Okay, hold on. We're going to go to the C drive. Okay, we're going to create a new directory there called QQQ for whatever reason. Okay, so within QQQ, it's going to name each one starting with seek. You can change this to whatever you want, underscore, and it'll place an index number afterwards. So let's go to here. Let's go to QQQ so we can watch. Okay, and let's say view large icons. So then I hit Control C. It'll take a screen capture. And then I can fly in, Control C. It'll take another screen capture. I can nose up and then go backwards so that I'm now falling below it. Control C will create another screen capture. So you can create a whole sequence of screen captures. So that's, now we also have the ability to capture screens programmatically during simulations. That's where the majority of our images are captured from. This is just a manual method in case you need to get something quick. We talked about that. Okay, so I'm not going to go through these. Everybody knows the drill on these. I've been trying to update this guy. I got all the updates done. I'm having trouble loading it up, but I'm going to hopefully get it done tonight. We'll see. Yeah. Thank you, everyone. No more voodoo physics.